They're all fast. They're all
Is this the Q equals MCAT?
All right. Good morning, everybody. As much as I would rather teach you about video game physics today, we do have to do thermodynamics. Oh, the exam. I forgot to post this morning. You guys can like kind of talk freely now. Okay. Everybody came, all that kind of stuff. I sorted out the one case that didn't come. You can like just don't worry about. You can cry on each other's shoulders, right? You can do all that kind of stuff. Compare notes. I do warn you though, right? Because I'm not going to talk about it until next Tuesday. I do warn you that oftentimes students will convince themselves that they got it wrong when you still got it right. In talking to others, right? You'll convince you, just like a multiple choice question, you convince yourself out of the right answer, right? Okay. But as you talk, right? Okay, and compare notes and all that kind of stuff, just keep that in mind, right? You will have the full story on Tuesday. I'll have them graded probably by today. I really don't want to do it tomorrow. Tomorrow my 4A students are taking their exam, so I really want to try and get them graded. First 4A exam is rough? No, it isn't. For them it is. But in hindsight, no, I know. They're all panicking. They're all like, right? They'll be all right.
Yeah, I was like, no.
Unless tonight I'm like have a personality change and come out swinging. All right. Thermodynamics. Why thermodynamics? Thermo. What's that mean?
Heat.
So heat. We're talking about energy that, for really the first time, it doesn't come from any mechanical sources, right? And so we're talking about the energy that things have because of their molecules wiggling, all that kind of stuff. Dynamics. What does that mean? Motion. So there is where we really differ from the chemists, okay? When physicists and engineers talk about thermodynamics, we're talking about how do we use this energy to make things happen in the universe. Chemists are all about, well, how does the energy affect our little system here? And so this is where the first frustration is going to come, especially if you're a chemistry major. We do everything the opposite way the chemists do. And in my arrogance, I, of course, say, the chemists do it wrong! But they're not wrong. They do it the way that it makes sense for them, and that's fine. So what I want you to do is not a quiz. Turn to your neighbor and tell them the difference between these three things. You can define them for each other, whatever, but really, we want to know what these things are and how they're different. Go. All right, that's enough. Way too much time in thermodynamics. All right, so let's start in the middle. What's temperature? Measure of the average energy per molecule in something. The key word and that you need to focus on when it comes to temperature is that word average. And temperature is different from thermal energy because thermal energy is what? It's not an average, then it's the total. Thermal energy tells us how much energy is in something, in a system. Temperature tells us the average energy per molecule in that system. And what is heat? Let's see. But what is it?
How much the stuff is moving?
Is it maximum?
Okay. Say it again.
How much the stuff is moving?
It's transfer of energy. Heat is energy going somewhere, in or out, but it has to be going. You will hear the term heat transfer. It's in your book. I'll use it. It drives me up the wall because heat transfer literally is energy transfer. Objects do not contain heat. What do objects contain? What do they have? Thermal energy. And when that thermal energy is transferred from object to object, we call that transfer heat. Which of these objects, right or left, has a higher temperature? The one on the left. How can you tell? The thermometer's longer. Okay? So it has a higher temperature. But which of these two has more thermal energy?
Right.
Does it depend?
Could be the same, depends. But all things being equal, the one on the right has more thermal energy. Even though it has a lower temperature, on average, the molecules on the one on the right have less energy. The one on the right has way more molecules in it, right? So, what has more thermal energy? A coffee cup that's got hot coffee in it, or an Olympic-sized swimming pool that's frozen solid? The swimming pool by a long shot. There's just way more molecules. Each of those molecules has a lower energy than the molecules in the coffee cup. The coffee cup has a higher temperature. But because there's so many more molecules in the frozen swimming pool, there's way more total thermal energy in that swimming pool.
So it's more of a like a quantity kind of thing?
It is, right? And the trickiness of averages, and now we're having to talk about statistics, and I hate doing it. Okay, so yeah, temperature is a measure of an average, whereas thermal energy is the total. Which of these have more heat? Wrong question. What is heat? It's a transfer. It's not something that's contained, right? They're both sitting on the same hot stove. They both have the same surface area of contact. So the heat, the energy transfer into both of these systems should be identical. Not because of what they contain, but because they're sitting on a hot surface. And energy is moving. What's temperature? Is screwed up. Why is temperature screwed up? Because there's really only one temperature scale that matters. The Kelvin scale. Okay? The Kelvin scale been out of shape. It's absolute zero is too low. You can't ever reach it. Blah, 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 blah. But you know what? It should just be the standard scale, right? I understand, put 0 where water freezes, because human beings and water and weather and all that kind of stuff. What happened to the Fahrenheit scale? Well, it wasn't America this time. We commit the sin of propagating it and continuing the tradition of terribleness that is the Fahrenheit scale. Like, who sat down and, 180 degrees between freezing and boiling was a good idea? It's dumb. At least Celsius. What's the same between Celsius degrees and Kelvin degrees? The degree. right? A 1 degree change on the Celsius scale is exactly equivalent to a 1 degree change on the Kelvin scale. The only thing we are arguing between Kelvin and Celsius is where to put 0. 32 is the freezing point of water? I do know the reason. I could give you the history, but ask me later. Oh yeah, this picture. What is absolute zero? No motion. Okay, quantum mechanics. Quantum mechanics is my answer to that completely inane thing that they teach you in chemistry. Temperatures have molecules are wiggling. You guys are also talking about atoms or springs or something. Fine. It's a good approximation. It gives us things like Teflon and plastic. So great. The thing that frustrates me is not that people get it wrong. It's that even though chemistry is just living this big fat lie, they have an excellent explanation within the confines of chemistry that they always ignore. And so they tell you things that stop moving. What happens to a gas when you heat it up? It gets bigger, right? More energy. What happens to a gas when you cool it down? What's the smallest volume a gas could have? 0. Now you're saying, well, wait a second, Mr. Bill. The gas has molecules. Molecules can't have 0 space. In theory, is there a lower limit on the volume a gas could have? 0. Is there an upper limit on the volume a gas could have? Size of the universe. Fine. Good luck. Okay? But the point is, we can cause that gas to condense and squeeze down into space, treating it classically, no quantum mechanics required, right? And if you go and you take that ideal gas and you lower its volume until it achieves 0, you will be at the temperature called absolute 0. What is absolute 0? It's the temperature you need for a gas to have 0 volume. Isn't that so much better? There's no wiggling. This is straight, what is this, like Boyle's law or something like this? Ideal gas law is what this is, right? Okay? And it's beautiful, and it's wonderful, and it makes classical sense, and you don't need quantum mechanics for it, and why don't they do it this way? Anyway. That's why physicists like Kelvin scale, because everything gets to 0. We're done. Oh yeah. What happens, we talked about, what happens to anything when you heat it up? It expands, right? Okay. By that, we mean that the space between molecules gets bigger. Okay? Now, from a thermodynamics point of view, of course, the molecules are all wiggling around. Like are the molecules in the surface of this desk, are they solid? Are they frozen? No, right? They have some amount of wiggle to them, right? And we'll get into the phases of matter later, but there's energy associated with all the wiggling going on down there, right? And if I were to heat this desk up, the space between molecules would get bigger, right? If I cool it down, it would contract. And we can see that thermal expansion and contraction in structures. Why is this bridge not attached at one end? Actually, both ends. The part of the bridge, I don't know what side it is, we'll assume it's the uphill side, right? This side of the bridge is hanging in the air made of asphalt and concrete and rebar, right? This part of the bridge, which technically isn't the bridge anymore, the ground, right, where the road meets, that's earth and all that kind of stuff. And at a given temperature or exposure to a temperature range, the rate at which the earth expands and contracts is different than the rate that the bridge, made of metal and concrete and stuff, expands and contracts. And so they put an expansion joint in there that allows for the bridge to expand. Because if you just kind of bolted it all to the earth, what would happen? As soon as the temperature changed, the bridge would buckle. In Iceland, they get a lot of their energy from geothermal sources. They just drill holes in the ground and steam comes up out of it. Okay. Do you see those pipes? Do you see how they're hooked around? Okay, and they're doing these curly. Why don't they just? Wouldn't it be cheaper to just put the pipe on the bottom and go? Why go up and around? It's Iceland. It's cold in Iceland in the winter, and in the summer it's less cold. Right? But it's warmer. Right? And so they got to go through temperature changes that are pretty extreme. What do you need to make sure your pipes don't do? Explode as they expand and contract. I went to Iceland on a study abroad. I was a teacher in the study abroad, and we got to tour a geothermal plant. We were doing geophysics of Iceland. And we got these tours, and they run pipes in Iceland from the geothermal plants to town. 50, 100, 200 kilometers away. They are so good at what they do that they will drop less than a centigrade degree over 50 kilometers of pipe. Yeah. Do you know what they insulate their pipes with? Pumice. The volcanic rock they've got in there traps a ton of air. They grind that up and they make a new sort of, they cast the pumice as they go, molten pumice as they go. Okay, pumping it there. And so the inner pipe is, I don't know, that big. And then the outer layer of pumice is like this big. They're just using the rock on the ground, right? The machine just scoops it up as they go, melts it, and casts the pipe, right? Okay? But every once in a while, they'll have these big loop-de-loops, okay? Either horizontally in the ground or vertically in the air to allow for the expansion and contraction of the pipes as they go across the countryside. Iceland's amazing. This is what happens when you don't take into account thermal expansion. This was a train track, I believe, in China, where the engineers got the bright idea, oh, we could just cast the train, like the track itself, we'll just cast it molten iron as we go, and the machine would just run these things down, rather than having these bars that they gotta, and the machine would just go along, right? Well, what they failed to do was to put expansion joints. And so as soon as it got too hot, what happened? The train tracks buckled. They had nowhere to go. They couldn't expand along their length. And so they got longer in the other dimension, right? Okay, to do the expansion that they needed to do. So, yeah, that is not a good train track. That's what you learned today. No, it's not even a good roller coaster track, because that's an accident happening right there.
So,
Okay, yes.
with multiple expansion and contraction, would it have
Yes. So, but that's for your materials class taught by Dr. Orff here at President College. Let's do quiz. I'm going to guess that those of you that took chemistry, okay, are about to dread the next part. Because in chem, is this Chem 1A where they do calorimetry?
Yeah.
And keeping track of all the little Q's and things like that? Now, of course, chemistry is not a prerequisite to this class, and I should never make the assumption that you've had chemistry, but I probably won't do that anyway. So if you haven't had chemistry, be grateful. It's probably coming. But I'm going to try to do this from the point of view of somebody that's never heard of it before. So if you haven't had chemistry, you're actually at an advantage because you are not tainted. Okay? And what I mean by that is chemists do this weird. Now, I'm sure it works for them. I'm sure they've got good justifications for why they do it. But chemists are sloppy with their science. Okay? Calorimetry, the measure of heat transfer and what heat does in systems, is as simple as conservation of energy. Conservation of energy is something that I can ask you to remember, since Physics 4A is the prerequisite. But let me explain. And for those of you that have had chemistry, you're at a disadvantage because you're about to see a different way of doing the same thing, which means your brain is going to be confused for a while. Oh, good. These are German candies, okay? And you can see what unit that they are expressing the energy that is contained in this candy. A kilojoule, okay? What's a joule? Diamond or no, Joule? It's a unit of energy. We encountered them in Physics 4A when we were doing kinetic energy, potential energy, things were measured in joules, okay? Thermodynamics is all about energy. The energy contained in molecules, in a substance, because it has heat or cold or whatever in it, right? So when we measure in kilojoules or calories with a capital K or a capital C, okay, a student sent me this on vacation one year. She was vacationing in Mexico. We know this is pre-pandemic. And she got so excited about her coconut water can, right? Because what is it listing? Energy in kilojoules first. The way it should be. And then in kilocalories. What is going on here? What is a calorie? What's a calorie?
Unit of energy.
It's something that Americans like focus on, and we get all bent out of shape about how many of them we're having, and blah 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 blah. Blah, right? But what is it?
It's a heat of something with water, 1 degree.
Okay, you're really close, Jeff. The definition of calorie, and this is one of those things that I wish I just didn't know. The definition of calorie is the amount of energy it takes to heat 1 cubic centimeter of water, or in other words, 1 gram of water, 1 degree Celsius, between 14.7 and 15.7 degrees. Why are they being so specific? We just talked about it. What happens when water gets cold? It gets denser until it freezes, and then it gets less dense because water breaks what the universe is supposed to be doing. In a good way, we'll talk about that. So they specify the temperature range to make sure the density stays consistent, right? From definition to definition. But the idea here is that the calorie is a measure of how much heat transfer takes place, how much thermal energy is required to cause a temperature change to happen. A calorie happens to be equivalent to 4.186 joules. In physics, we use joules. We don't use calories. But that is a lowercase c, different from an uppercase calorie. What's the difference? This is a kilocalorie. Okay? And also known as a dietary calorie. So when the Snickers bar says that it has 186 calories, let's not question how I know specifics. It says it has 186 calories. What do they mean? They mean dietary kilocalories. In other words, that 186,000 calorie Snickers bar. What did I just do there? 186,000 scientific calories. Because the dietary one is a kilocalorie. You have to do 10 to the 3 on it. And so now you're sitting there going, now I know why I can't lose weight. Because it says 186 calories, but it's really 186,000 calories. Why do they do? Why?
A lot of zeros.
It's a lot of zeros. Dietitians got tired of writing 10 to the 3 all the time. So you can't blame them, right? Okay, but we got to be careful. When it comes to dietary information, it's a kilocalorie, okay? Multiply by 1,000 to get the true scientific calorie, which is that many joules. But it's okay. When they tell you that you need 1,500 to 1,800 calories per day in your diet, okay, that's really how many? Kilocalories. So I need 1.5 million calories. So bring on the stairs.
This is more of a chemistry question, but how come when you freeze water it expands?
Okay, we'll get there. We'll get there. We'll get to the phases of matter. I don't remember when, but it's coming up. Yeah. It's because water's awesome. So just be aware. And if you need to know what your calorie intake should be, whatever, you count calories, all that kind of stuff. The first dietary advice from a physicist. The first thing is check what you are eating, right? Try to make it veggies and fruits and things like that. It's not, yes, calories matter, but it probably matters more that you're eating good food as opposed to processed food. Then you can start counting calories and all that kind of stuff. And if you want to lose weight, what do you have to make sure you're doing? Burning more than you're taking in, right? Okay. Because what's the body going to do if it gets more energy than it needs? Store it. Working on my food storage. So, yeah. And don't get bent out of shape about it, right? Americans are horrible when it comes to body image because we're stupid. We use freedom. We use Fahrenheit. What the heck is this? Okay. I have to center myself because, again, chemists do this wrong. What is specific heat?
Capacity to absorb heat.
It's the amount of energy required to take 1 gram of the substance through 1 degree Celsius between 4 degrees, right? So it's just like the definition of the calorie. It's just, instead of the word water, what do you insert? Thing, right? Whatever substance it is you want. So here's the specific heat capacities of various things, right? So if you ever want to know specific heat of ethylene glycol, I don't know why you would want to know about antifreeze. Okay? That's what ethylene glycol is, antifreeze. One of the main components of antifreeze. Okay? So there's water, right? 4.186. They rounded a little bit, right? Okay. Calories per gram Kelvin. What kind of unit is that, right? Which is the physics unit up here? Obviously, joules per kilogram Kelvin. That's where we're going to live. So those of you that want to play in calories, stop. Okay. And you're like, but the numbers are small. Yeah, fine. Numbers are small, but the numbers are dumb, right? You just do everything in symbols and then put the numbers in the end. You're fine. So there's a key concept here with calorie and with specific heat capacity that we can go back to physics 4a to try and help us understand conceptually what's going on here. Specific heat capacity is thermal inertia. I'm done. Thank you. Have a good day. What's inertia? It's resistance to changing motion. The more inertia something has, the harder it is to get it to accelerate, right, in mechanics. Thermal inertia would be how much something resists changing its temperature. So the more thermal inertia something has, the more energy you need to give it to get it to change its temperature. That's what specific heat is. It's a measure of thermal inertia. So the higher the specific heat, the more energy you need to change the temperature of that substance. And on this list, which one is the highest? Water. By a long shot. By like a factor of 2, right? Ish. Like, water takes a lot of energy to change its temperature. Whereas lead, right? Silver, right? Okay? These things don't take very much energy at all before they go, I'll change my temperature, no problem. What's the average temperature in San Francisco? Like year round? 65, right? Like, when it gets over 75 degrees in the Bay Area, people heat wave, right? Okay. What's the average temperature? So okay, let me say it this way. In San Francisco in the wintertime, the average temperature is about 65. In San Francisco in the summertime, the average temperature is about 65. Like, there's there's of course weather and differences and climate change and all that sort of stuff going on. But in general, right, the variation between temperatures from summer to winter in the Bay Area is very low on the peninsula of San Francisco. Compared and contrasted to Fresno, where we will see 115 degrees in the summer and 55 for a daily high, 50. What was the high yesterday? It was 52, something like that, right? That's more than 50 degree variation, right? Summer to... Why? Water. San Francisco is surrounded on 3 sides by water. And where does all of the sun's energy go? Into heating up the water. Dirt has a much lower specific heat, meaning that its thermal inertia is much lower. So if you want to change the temperature of dirt, it's not hard. Shine some sun on it, boom, you got 115 degrees. We don't have the water. Millerton Lake doesn't count. We don't have a lot of water, okay, around here to mitigate the energy that's coming from the sun. And so we'll go through these large swings and variations in our seasonal temperatures compared to places that are near the coast or surrounded by water and all that kind of stuff. Which of these materials is best to cook with?
It's probably lead.
Not lead, or mercury, or ethylene glycol. The package of noodles does not say boil ethylene glycol. It's a trick question, because the answer is it depends. What are you trying to do? If I want to deep fry something, you can bet that I'm going to want to do it in an aluminum pan. Because not only is the aluminum harder to heat up, it takes more energy to change its temperature, which means it's going to have this inertia to maintain its temperature longer. And when it comes to deep frying food, you want to stop big changes in the temperature of your oil. You introduce the food, the temperature of the oil is going to drop, but you want to bring that temperature back up more or less as fast as you can. If you let it go too far, soggy French fry. But if I'm sauteing mushrooms, anybody getting hungry? Cooking class with Mr. Balogh. If you're sauteing mushrooms, then I want to do it actually either on an iron or copper would be better pan, because I can get fast temperature changes. I can go to sear and pull back on that sear if I need to go, and then back to sear very quickly. I'm doing that on an aluminum pan. There's going to be these hesitations, okay, in the cooking process. So that's why some pans have copper cores and then are surrounded on the outside by stainless steel. There, you're getting a majority of the mass of the pan as copper, so it's quick to change its temperature. But copper is also a soft metal and kind of expensive. And so you clad it in the iron of the stainless steel to give it structure. And the iron is 0.47 and the copper is 0.39, so you're kind of close, but you're taking advantage of rapid changes in things. And why is it that we cook our noodles in water? We've got to rehydrate them, I'll give you that. The temperature of that water is going to stay more or less the same. Dump the noodles in, it'll cool off a little bit, but it'll rebound pretty quick. Because it takes a lot of energy to change the temperature of water. It takes a long time to get water to boil, doesn't it? Okay. We're doing a lot of concept. Let's do some maths. As if we were in Great Britain. The way that you keep track of energy going places is through knowing the mass of the material that you have, its specific heat capacity, lowercase c, and I'm not responsible for that. I know it looks like a calorie, but it's just that's the symbol for heat capacity and the speed of light. Times the change in temperature that something goes through. A lot of times you will see this equation written as delta Q equals mc delta T, just to sort of emphasize the idea here that we're changing energy. So Q is referred to as the heat. Q and delta Q are more or less synonymous in physics. Okay? So we'll be chasing Q's around, meaning that we're looking at heat transfer. We're looking at energy going places. We know that heat is happening because temperature is changing. Keeping track of where the energy going is what calorimetry is all about. Calorimetry is keeping track of thermal energy moving in and out of things within a thermodynamic system. And I keep dropping this word system. What does that mean? It's a collection of things put together, and everything that's not a part of the system we are ignoring. Okay? And so you want to be careful about what is in your system or what is considered part of your system. And we're going to formalize this a little bit more when we get to phase changes and work done on the system and that sort of stuff. But let's take it as an example here. This is an example of calorimetry, doing a calorimetry problem where we're going to keep track of energy changes. And what we're going to try to do is find the final temperature, right, of this system. So from this problem, name the elements or parts of the system we have here. What do we got? We have a metal sample, right? What else? A copper cup and some water. Are there any other objects? No. So those three things together are considered the system. Are we going to worry about the Bunsen burner that the thing was heated up with? Are we going to worry about Mars? No. Are we going to worry about the insulation that's around the copper cup? No. It's not a part of the system. And what we're going to do is we are going to make sure that the total sum of all of our changes in energy is going to add up to 0. What we're saying in that statement is that any energy transfer that happens between the members of the system and not the rest of the universe. In other words, we're going to have a perfectly insulated system. If it weren't perfectly insulated, we couldn't say it's equal to 0. I think looking ahead, you already know. Which of these objects is going to lose energy? The sample, right? It's the hotter thing, right? And so its temperature is going to go down, and the temperature of the water and the copper cup are going to go up, right? So we know these things. And if this were chemistry class right now, we start tying our knickers in knots over what's negative, what's positive. Don't go. Nope. Don't go there. Everything equals 0. Trust the physics. Don't put signs on things that don't need signs. What do I mean by that? In chemistry, you would probably do Q hotter things equals negative Q colder things or something like that.
Yeah.
No, that is horrific. That is a train wreck waiting to happen. Okay? This is the way. This is the way.
So we don't use system and
We will. We're getting that second law of thermodynamics stuff. Notice that the total sum of changes in heat has to be the Q's of the hot things plus the Q's of the cold things, right? Equals 0. And if I move the Q cold over, that's where chemistry gets it from. They never tell you this, or do they? No. Okay. And then there's some mystery about which sign do I put on stuff. There's no mystery. There is no mystery whatsoever. And I will now demonstrate why there is no mystery. The system consists of, and I can draw a picture if I want. Here's a copper cup. Apparently turned green already. There's some water. And here's my unknown substance. Right? They're all put together and they're going to come to thermal equilibrium. So that means that I have to have Q of my sample plus Q of my cup plus Q of my water, and all of that has to add up to 0. I've dropped the deltas here. Are you okay with me dropping the delta? I get tired of writing the deltas. Physicists just, it's fine. It's Q, it's delta. It's always, anyway. Okay, what is the Q of the sample? Don't overthink this. It's the mass of the sample times the specific heat of the sample times the change in temperature of the sample. Did I put a positive or negative sign on this? No, because I don't have to. Plus, what's the Q for the cup? It's the mass of the cup times the specific heat of the cup times the change in temperature of the cup. What's the Q for the water? It's the mass of the water times the specific heat of the water times the... Kindergartners can do this, right? This isn't just copy and paste. Okay? How is it that 3 positive things can add up to 0? They can't. One or more of these things needs a minus sign on it. But am I going to put the minus sign on there? No. I'm going to let the deltas do the work for me. We know one of these things is losing energy. Which one is it? It's the sample. So the delta T of the sample. Do we know anything about the... So we know the mass of the sample, right? And we know the specific heat of the sample.
No.
No. We know the final temperature. We're looking for the specific heat. So this is our unknown. That's our target right there, right? Okay. What is the final temperature of the sample?
25.
It's 25. And what was the initial temperature of the sample? Minus 100. What is 25 minus 100? Negative 75? All done. I don't have to sit there and guess which is positive and which is negative and get it wrong. Let the deltas do it for you. Not the airline. These are all numbers. We know the mass of the cup. We know the specific heat of the cup. What's the final temperature of the cup? 25. What's the initial temperature of the cup? 20. Ooh! What's the delta on the cup? It's positive. What does that mean? Gave up energy. Gained energy, sorry. Gained energy. That's positive. Mass of the water, specific heat of the water. What's the final temperature of the water? 25. What's the initial temperature of the water? 20 equals 0. There's only one unknown in this equation. And this is the green arrow pointing straight at it. So what do you do now? It's algebra, right? Stuff. I'm not going to do it because I don't want to. The specific heat of this unknown, this sample, is equal to 438 joules per kilogram degree Celsius. Now, degree Kelvin, degree Celsius is the same down there because it's just a degree. Do your temperatures need to be in Kelvin for this? No, it's a delta temperature. And delta temperature on the Kelvin scale is exactly the same as a delta temperature on the Celsius scale. The Celsius and Kelvin degrees are the same. They argue about where 0 is. But when you go from 1 degree to the next, it's exactly the same distance on the scale.
But you need to know the specific heat of the coffee cup.
Yes. It doesn't tell us? It says it's copper, so you go ask Google or look in your book. There's tables of the specific heats of these things.
So if you were given temperature in Fahrenheit, would we have to convert it?
Now you got to convert it into Celsius. Yes. And there's equations for that too. I didn't cover them because they're done. 5/9 times 9/5 or something. Alright. Alright. So make sure you're working in at least Celsius and not Kelvin. Celsius is okay here. When we get to ideal gas law, we're going to have to be in Kelvin. Okay. But Celsius degrees are okay here. Kilograms. What must you put your masses in as? Kilograms. Standard units in equals standard units out. Not grams. Even though everything's given to you in grams. So 100 gram samples, how many kilograms? 0.1. 150 grams is 0.15. Right? You're going to be doing this conversion a lot. And then to find the specific heats, I'll even capture this one. So it'll end up in the PDFs if you want this particular table. Okay? Covers just about every material you're going to hit in any of the problems. Okay? Which of the numbers are we going to use? First column, second column? First column. Now, if you want to do everything in calories per gram Kelvin, that's your business. Okay? But even though this is in joules per kilogram Kelvin, it's okay to use Celsius. Why? A degree is a degree on either of those scales. Right? And it's a delta. As soon as you see the temperature, now you better make sure you're in Kelvin. But if it's a delta temperature, Celsius or Kelvin, both will work. That was the other thing we were supposed to find this video. I did it. Right? Like, don't overcomplicate this. It's conservation of energy, and as long as you just put the right numbers in, you're going to get the right answers. Like there's no mystery about which sign do I put on things, because it's built in there. Until we get to this. What are the phases of matter? Solid, liquid, gas. Plasma. Keep going. Not weird physicsy ones. There's two weird physicsy ones now. Bose-Einstein condensate. The most recent one is time crystal. Okay? Doesn't it? I mean, who knows what a Bose-Einstein condensate is? But time crystal, I'm on board. Okay? Right? So the sixth one, we're still physicists are kind of arguing about, but we physicists were able to synthesize time crystals in the lab under very high pressure. It's very exotic from that. So we really don't need to worry about it. You don't even really need to worry about Bose-Einstein condensates until we get to quantum mechanics, and then we'll worry a lot about them. So really, we've got those primary four, right? Okay, solid, liquid, gas, plasma. Plasma is a gas. It's just that it's made up of
Electrons.
charged particles. Okay, so it's a gas of charged particles, whereas a gas can be either plasma or neutral. Right? Why? Why is a solid a solid? Why is it liquid liquid? Why is it gas a gas?
Space between the atoms.
Molecular structure.
It all comes down to energy. It's always energy. If you don't know the answer, it's the square root of 2g. So, talk to me about the kind of energy that molecules or atoms in a solid have. Is it like free and liberated and can go wherever it wants, or is it really constrained? Very constrained. Okay. Liquids? A little bit looser, right? Less constrained in terms of the types of energy it can have. And then for gas? Whee! Right? Okay. So I am going to demonstrate something, and I apologize in advance for the emotional trauma that you're about to experience. Because I have no greater analogy than this when it comes to the phases of matter. Okay? Let's, and I don't, is clubbing still a thing? Is it still kind of, you go out to the dance club or nightclub or the bar or anything and people are dancing?
Yeah, but we don't call it
I know you don't call it, I'm old. Okay, but so let's go back to the 1980s. Okay? And you go to the dance club, right? Okay, and let's say you get there peak hours, right? When like everybody's trying to get in, right? And the bouncers are just hauling drunk people and throwing them in the street, right? Okay? When you get to that dance floor, what are your dance options? Again, picture like everybody's crammed in. Like what can you do? Right? This is about it, right? Okay? Right? But you are so packed together, right? That you basically can only do this, right? So let's say instead of getting there at peak time, you got there a little bit early. So there's still quite a few people, but there's a little bit more room on the dance floor. Now what are your options? You can do this, right? Still. But what you can add to it is what? Right? You have room to turn, you can vibrate, and you can rotate, okay? But again, you're still restricted. Okay, let's say you are Mr. Bailey and you get there way too early because your bedtime's 9 o'clock. Okay? And you've got the dance floor to yourself, right? So you can really bust some moves. What are your options? You can vibrate, right? What else? You can rotate, but you can also translate. And there's the emotional trauma part. Because you had to see me dance. Okay? Which of those is a gas? The last one, right? Because all three modes of vibration or types of energy are available. The vibration, the rotation, and the translation. They're all forms of kinetic energy, right? Because they're energies of motion. But molecules that can do those are gases. Which one was the solid? The first one, where it's just limited to vibration. And then which one was the liquid? Where you can both vibrate and rotate. This is how physicists determine the phases of matter. It's not some magical, mystical temperatures, although we're going to get into that. It's all coming down to the types of kinetic energy a molecule of a substance can have.
So would plasma kind of be the same thing as the gas, but you're on fire?
Yeah, but no, because you get very cold plasmas, and I can't point to them anymore because, well, they used to be right there. Those are LED lights now, so now quantum mechanics is right there. But when they were fluorescent bulbs, those are cold plasmas. Plasmas aren't necessarily hot. They're just gases of charged particles. So the particles have all of that plus the energy of charge associated with them.
I was thinking more just you'd be a lot more energetic if you're on fire.
Yeah, we're going there. It's quantum mechanics. We're going there. All right. So changing the phase, right? Getting something to go from solid to liquid to gas or anywhere in between requires changing what? Energy. You've got to change the energy in order to change the phase. But back in the day, when thermodynamics was all the rage and train steam engines were a big deal, these concepts of types of energy, vibration, they didn't even know that electrons existed. They were still arguing about whether atoms were a good idea, right? And so heat and thermal energy was more sort of this mysterious fluid that was in stuff. Like, they knew it wasn't a fluid, but they sort of modeled it as a fluid, and it flowed places and all. It's weird. Okay, I should be less critical of history because, of course, I stand on the shoulders of giants and I can look back. They were doing brilliant work, okay? It's just, it's in the past. Can we let go, please? Like, seriously? But no, we can't because we have graphs like this. The amount of energy that's required to change the phase of a something is referred to as the latent heat. Latent is an old-fashioned fancy word, like Latin word for hidden. Because what they discovered was, as you raise, say, take a pot of water, put it on the stove, you start boiling the water, right? Well, it doesn't immediately boil. Its temperature goes, whatever room temperature is, up to 100 degrees. And as soon as it hits 100 degrees, what happens to the change in temperature? It stops, right? And instead, the water starts evaporating, like steaming, it's boiling, right? Like water vapor's coming off of it, right? But man, as long as the water is boiling, it's going to stay the same temperature. And so, what happens if you turn the heat off? No, like it immediately stops boiling. Like it, boom! Unless you got like an electric burner that stays hot for 10 years. Right? Okay? Like you remove the source of heat and the boiling like immediately stops. And then it begins to cool down. Right? Phase changes, changing from the liquid water to the gaseous steam, takes energy. And so energy is being dumped into the system, but the temperature is no longer changing. All the temperature is going into changing the phase. And so they called it latent heat or hidden heat because they didn't understand where the energy was going. Like they didn't have this concept of atoms and molecules and the energies that they have. Nowadays we understand that energy is going into convincing those molecules to go from this, right, to beginning to translate. And translation requires a lot of energy, right?
So what about superheated water?
What about it?
It could hit 274, but in a certain pressure.
Yeah, but the pressure is keeping it as a, there's a whole bunch
So are
of...
we talking about like room pressure?
Yeah, we're just talking about standard pressure.
Same thing with pipes and freezing.
Yep, pipes and freezing and all that. But water, okay, water. Water. Water is its most dense at 4 degrees Celsius, 278 Kelvin. Colder than that, and it expands. Warmer than that, and it expands. Water is the one thing that breaks the rule when it comes to density and thermal expansion. I know right now that the temperature at the bottom of Huntington Lake is 4 degrees Celsius. I have to go out and measure it. How do I know right now the temperature at the bottom of Huntington Lake is 4 degrees Celsius? It's frozen on top because it's wintertime, and the densest water will go to the bottom. And water is its most dense at 4 degrees Celsius. Why do the fishies not die when the lake freezes over? Because frozen water, water at 0 Celsius, is less dense than liquid water at 4 Celsius. You would not be here if this was not a feature of our universe. Now, as to why water molecules do this, 3 words. 1 word, 2 words. Van der Waals forces.
Oh.
Explains everything, doesn't it? No, it explains nothing. The truth is, a water molecule looks like Mickey Mouse. And that's why. Okay, so, I don't want to go there. What is this graph trying to tell us? Okay? It's trying to tell us that energy is required whenever we are changing the phase of something. And so what I need you to do, what I want to teach you is that you should look at this as like stairs. Okay? As we go up vertically, we're getting hotter. Time is on the x-axis, but hotter, we're going up the stairs, right? And so, if we take an ice cube at negative 20 degrees Celsius, it comes out of your freezer at about negative 15 Celsius, okay? Because your freezer is 0 Fahrenheit, which is way below 32. So the ice cube comes out of your freezer at negative 15 Celsius, and we put it on the desk. Before it can melt, what must the ice cube do? When does water ice start turning into liquid ice? At 0 Celsius. It's at negative 15, so what does it need to do first? It needs to get energy to get up to 0. And once it gets to 0, what now happens? We climb the stairs, we got to 0, and now we're going to stay the same. Time's going to go by, but the temperature's not going to change. Why?
It's melting.
We're changing the phase. We're melting the ice. And then once the ice cube becomes all water, let's say we got it on the stove, right? We're continuing to dump heat into it. That water will then begin to change its temperature. Why? Well, we're adding energy and it's water, right? And it will gain that temperature until it gets to where? 100 Celsius, where boiling will happen and the phase will change again. It'll change from its liquid state to its gaseous state. We call, what is gaseous water? Steam. Okay? Water has special terms, everything else doesn't. Okay? So, now that we've got steam, let's say we can collect that steam, we don't let it out into the room. Don't do this at home. It's called a bomb. But if you are able to contain that steam and continue heating that steam up, it will just increase its temperature. Okay? But what happens if we start taking energy out of that steam? It will condense. Okay? In a process where it goes from steam to liquid, from steam to water, or from gaseous to liquid state. It's called condensation. Okay? But as all that steam converts back down to water, the temperature will be 100. And as soon as we've got all that steam back into water and keep pulling the energy out of the system, the water temperature will drop until it begins to freeze. In which case, what temperature will it be? 0 until it freezes. And after it freezes, it will continue to drop its temperature. So, phase changes require these periods of time where we're not changing, there's no delta T's involved, but energy is still being added to and taken out of the system. And oh my gosh, what is this? This is a table of the latent heats of various substances. And there are 2 latent heats associated with the 2 main phase changes of matter. The 2 main phase changes are going from solid to liquid, and the other one's from liquid to gas, but you can go both directions. And so, confusingly, there are 2 terms. There's the latent heat of fusion and the latent heat of vaporization. The latent heat of fusion always happens when you're going from solid to liquid or liquid to solid. Fusion, putting together, right? Vaporization happens where? When you're going from liquid to gas or gas to liquid. It's the same constant value at those 2 different points. So water, let's take a look at water. Where's water? Why did they put it in the middle of the table? Stupid, okay? Here's the melting points and stuff. The latent heat of fusion for water, 334 times 10 to the 3 joules per kilogram, okay? That number is the same as long as it's freezing or melting, meaning it's going from solid to liquid or liquid to solid. The difference is the sign that you put on it. The number for water, for the latent heat of vaporization, is 2256 times 10 to the 3. That would be the number that we use if we are at the phase change between liquid and gas. And depending on which way it's going, would determine the sign that we put on. This is the only time that you need to be careful of the signs. Latent heats are always calculated as mass times the latent heat constant. Notice the units of the latent heat constant. It's joules per, it's energy per mass. So if you take a mass and you multiply by this constant, you've got your energy. The plus or minus depends on which way you are going up or down the stairs. I kind of just always have this picture in my mind. Okay? If you are going up the stairs, you're adding energy to the system, you're going to put a plus sign on it. An ice cube needs energy added to it in order for it to gain the energy it needs to change its phase going up the stairs. But what happens if I'm taking water and I'm freezing it and turning it back into ice? I have to pull energy out of that ice cube. I need to get it to stop dancing like this and get it to only dance like this. So that's energy being removed from the system. And so energy. So what sign am I going to put on there? I'm going to put a negative sign on that one. In the whole analysis, and we're going to do it again, and I'm out of time to do the example, but I'll do it on Monday, but you can do it. You guys can do this yourself. All of this sum of the change in energies. Let me just show you let me get it started, okay? So we're at a party, okay? And we've got some punch, right? So what's our system? It's a thermally isolated punch bowl. And they don't tell me really anything about the bowl itself, so we'll just assume the bowl is a perfect insulator. They don't give me the mass. They don't give me the specific heat, so I'm ignore it. So we got the punch, which is water, okay? And then we add some ice cubes to it. I don't know why I drew in red, it's just fun. Okay? What would the delta Q's, the sum of delta Q's equals 0 look like? What do we have to keep track of? We have to do the Q of the ice going from -10 up to 0 degrees Celsius. We've got to change its temperature, right? So this would be like an MC delta T kind of thing. Got to change the temperature. And then, what do we have to do? We have to melt the ice, right? Get it to change its phase. While simultaneously considering the change in temperature, the MC delta T of the punch, right? And is this Q melt going to be positive or negative?
Positive.
Why is it positive? We're stepping up the stairs, right? We're on that flat portion, and we're stepping up the stairs, trying to get the ice to melt. But at the same time, what's the MC delta T? What's the sign going to be on the delta T for the punch? Starts at a higher temperature, ends at a lower temperature. It's automatically going to be negative, isn't it? So again, the only sign that you need to determine is when you have a latent heat. This ML, and latent heat of fusion or vaporization? Fusion, because we're down at the solid to liquid barrier, right? That's the only time you have to determine and pick a sign. It's the only time. Let the delta T's speak for themselves. But when it comes to the latent heats that you have in there, you got to make sure that you commit to the sign. Now, we don't know if this punch, does all of the ice melt? Because if it does, there would be another term we have to add on here. Once the ice is all melted, there would be an MC delta T of ice that's now water. It's changed its phase, but it's additional mass in the system that could be changing its temperature also. I will do this example in full on Monday. I'll back up a little bit, refresh you about latent heat, then we'll do the example with the latent heat in it. right? And then we'll move on and probably start chapter 19 at that point. I'm almost done with chapter 18. And we'll start chapter 19 on Monday.